Right, just one reaction. And then the next reaction is if we add one more HBr or excess of HBr, what's going to happen? So this is going to be a review, right? So the alkene is attacking the hydrogen, pushing the electron onto the bromine, and we are forming the more stable tertiary carbocation. And the Br minus will attack that carbocation and will form a di-substituted alkane or haloalkane. Now, what's the IUPAC name for this product? This is my 2,2-dibromo propane. And this is a haloalkane or dihaloalkane. All right, so this part should be review. Yes?
Will it be pretty clear, when you know to keep going, with the HBr?
Well, so the real question here is when we're talking about these kind of reaction mechanism, eventually we're talking about what is your reaction condition. Let's imagine you start with a acetylene, and then you're reacting it with HBr. If we specify the reaction is, well, one more of HBr added onto the acetylene, then we can probably stop here. But if in the reaction we say okay, we have excess of HBr, then we're likely to keep going until we have fully halogenated the double bond. All right, so it depends on how we describe the reaction condition. Or in organic lab, when you actually do the experiment yourself, it depends on how you set up the experiment. The other way we can ask you is, let's say we're reacting these two species together. You can choose to add acetylene to HBr or add HBr to acetylene. And that's going to give you a different product distribution. Right? Because if you're adding the acetylene to HBr, then when those droplets first meet HBr, you have excess of HBr, and hence overreaction can take place. Right? So the process of adding your reagents together is also important in organic chemistry. All right, and in our last lecture, we also went over nucleophilic substitution with a base. So in this case, well, we'll discuss this later on, but this one is using the acidity of the terminal alkylidine hydrogen, or the SPCH bonds. The acidity of the SPCH bonds means after we deprotonate it, we're going to form a terminal carbanion, and that's going to act as a very good nucleophile and strong base. So in chapter 9, where we're talking about nucleophilic substitution reaction, we'll be using that a lot. In our previous lecture, we were talking about this can react with a primary haloalkane. And in this case, this is going to be attacking the carbon next to the haloalkane and your halogen left, and we'll be able to elongate H3C, carbon, carbon, here we have 1, 2, 3, CH2, 2 of them. It's very ugly. All right. So, electrophilic addition of alkyne, in summary, they react very similar to electrophilic addition of alkenes. The only thing to pay attention to is to keep in mind, you want to control the amount of substrate you're using, whether it's a halogen like Br2 or a hydrohalogen. If we have excess halogen or excess hydrohalogen, we can overreact with my alkyne to form either the tetra halogenated product with HBr2 or with the dihalogenated product with hydrobromine. All right, a very similar reaction mechanism, electrophilic addition. Any questions for this part? Sorry, what's the question again?
Do we need to know that? Because then we'll come back.
This one? This one we went over in our last lecture. So this goes all the way back to here, which is upon formation of your, after deprotonation, you're forming this anionic alkynyl anion. This alkynyl anion will react with a haloalkane to form a elongated carbon skeleton. So this we discussed in our last lecture. Okay. Next reaction. What's the next reaction we discussed with our alkene? Well, hydration, right? So in hydration, remember we have 3 different conditions. We have the acid catalyzed hydration, which means we're forming a free carbocation. We also have hydroboration oxidation, anti-Markov-Nikov regioselectivity due to the concerted nature of the transition state. We also have oxymercuration followed by reduction. So the same thing applies to our alkyne reaction. So let's get started with the hydroboration oxidation. So in the hydroboration oxidation, for these internal alkynes, and we'll talk about why the internal alkynes works better. And let's see how that goes. So first of all, for internal alkynes, when we have hydroboration, this is the typical transition state we're adding. Remember, in the hydroboration, the hydrogen and the Br2 are added simultaneously onto your pi bonds. Now, for alkene reactions, the hydroboration is anti-Markov-Nikov regioselectivity. Because alkenes, well, when your boron add onto there, it will favor the sterically less hindered position. For alkynes, because my alkyne is a linear geometry, that means the regioselectivity control coming from the steric property is much less important. Because after all, it's only a linear molecule. You only have like 2 things around it, right? So in this case, when we're saying the regioselectivity of hydroboration of alkynes, we're looking at very little regioselectivity control. And my hydrogen and Br2 will add onto the triple bond via a thin stereochemistry, meaning my hydrogen and Br will add onto the same side of your alkene. Or these 2 will be cis to each other in the alkene that we generated. A few things will prevent this alkene to keep going. So remember, in our previous case, we were just discussing the overreaction with halogens and hydrohalogens. Now for hydroboration, because boron group is a highly Lewis acidic group, it will decrease the nucleophilicity or decrease how much electrons are there in my double bond. So the presence of Br2 will decrease the nucleophilicity of my double bond. And also, we're forming more sterically congested internal groups. So normally, hydroboration reaction will not overreact, meaning you normally do not have 1 more Br added onto the double bond if it is an internal alkane. All right. And that's the first step. Second step, once we form the alkynoboron or the carbon-boron group, next step is oxidation. Now, the oxidation mechanism is not necessarily required, meaning like for this one, I will never ask you to write out the full reaction mechanism from the CBr group into a OH group, but you need to know that under the condition of hydrogen peroxide and the base, the alkynoboron will undergo oxidation to replace that Br2 with a OH group. And this specific structure, we're going to spend a lot of time talking about. This is called a eno. So the name of eno is stating we have a hydroxy group or a OH group bonded to a carbon-carbon double bond. So whenever you see something like this, that is called a eno. All right, so whenever you see a OH group right next to a double bond, that is a eno group. Now, a eno group is not a very stable functional group. It can really quickly undergo tautomerization or they can be easily converted into more stable keto group. And when we say keto, we're saying either a ketone or an aldehyde. And the process of converting an enol into a ketone is called a tautomerization. All right. And let's look at the mechanism of the keto-enol tautomerization reaction and see how to write out what is happening to convert your enol into keto. So the keto-enol tautomerization can take place via two different mechanisms depending on its reaction condition. Under basic condition or under acidic condition, the keto-enol tautomerization can both take place. Now, in our hydroboration oxidation scenario, we're looking at a basic condition. So let's look at our basic condition first. So when we say it's basic condition, well, we have OH minus around. And we observe this entire molecule and thinking about what is my most acidic hydrogen in this entire molecule. The most acidic hydrogen is the OH hydrogen, right? Because we're forming an anion on the oxygen, and not only we're forming the anion on the oxygen, that anion is being stabilized through resonance. So the first step is deprotonation. What we're forming here is upon releasing of water, we're forming H3C, H2C, carbon, hydrogen, double bond, carbon, O minus, CH3. Deprotonation of the most acidic hydrogen. Well, obviously, there's a resonance structure coming from this one. And I shouldn't write this as a resonance. Sorry. And what is that resonance? Well, we can push the oxygen onto here and the double bond onto there. It's going to be a minor resonance structure, but after all, again, when we're saying resonance structures, we're saying there are coexisting structures representing the reality, right? So the reality is the overlap of both resonance structures. And in here, this is a very strong base, and it will react with your solvent, which is my water here. And protonation. And we're regenerating our base. All right, so if we look at this entire mechanism here, we started by using OH minus as our catalyst. We're regenerating this OH minus. So my OH minus here is acting as a catalyst. And in the enol-keto tautomerization reaction, we are transforming this enol, again, a enol is a hydroxy group neighboring to a carbon-carbon double bond, into a keto form where you have a carbon-oxygen double bond, and this is a ketone. All right, and this is a base catalyzed enol-keto tautomerization reaction. Yes? Well, you'll know the catalyst. So in this case, You know the base is present because observing the reaction condition of the oxidation reaction, we have a base present, right? So I do not have to specify that base is acting as a catalyst, but it's more or less, you know the base is present and a keto-eno tautomerization is taking place. So it must undergo a base catalyzed keto-eno keto tautomerization reaction mechanism. Again, this is one thing in organic chemistry. Like the important thing is observe the reaction condition and think about what is in my reaction mixture. What are available there for me to use as my catalyst or my reagent? And let's work on a different example, and we'll come back to questions after we finish this part. Now, we were talking about tautomerization under the basic condition. Right, so again, what is my tautomerization? We're talking about tautomerization as an interconversion between two constitutional isomers, right? So your ketone and the eno are two constitutional isomers. And we're saying the eno can tautomerize into a ketone or an aldehyde, right? So the keto form is typically more stable than the eno form, and hence the keto-eno tautomerization can proceed quite rapidly under, well, we went over the basic condition, also under the acidic condition. So let's look at the keto-eno tautomerization mechanism under the acidic condition, right? So we start from my eno. And now I have a proton around. And in this case, well, we're looking at the the acid catalyzed keto-eno tautomerization. We're having the double bond, the nucleophile on the oxygen attacking the hydrogen. And the first step is protonation. What we end up getting, HH3O, the acyl group, CH, double bond, carbon, oxygen, hydrogen, hydrogen, plus, and CH3. Likewise, this undergoes resonance. Or what we're doing here is we're pushing this one. Actually, I think I did it. I should do it the other way around. It's not your oxygen attacking the hydrogen. It should be your double bond attacking the hydrogen because that's the better nucleophile. Yes?
Where did the oxygen come from for the H2O? Like on your,
Oh, that should be carbon.
oh, sorry.
You know, some of them are like obviously typos. All right, so the double bond is attacking the H+, and we're forming a carbocation intermediate. And in this process, again, it follows our rule of favoring this one is, well, the secondary carbocation, a tertiary carbocation versus a secondary carbocation. So we're forming the more stable carbocation. And then we can draw resonance structures. So in this case, that's going to be a acyl group, CH2, carbon double bonded to oxygen, hydrogen with a plus sign on the oxygen. Now again, this is going to be a minor resonance structures because I know oxygen is more electron negative, but after all, both of the resonance structures will contribute to the actual representation of the molecule. And the next step will be deprotonation. To regenerate our catalyst. So what we end up getting and your H+ is regenerated. So this is why we say like the keto-eno tautomerization can take place under both basic and acidic conditions, but just via slightly different reaction mechanism. And why do we care about acid catalyzed tautomerization? Like what we said, right? So in the first reaction, when we're doing the hydroboration hydration reaction, we're having the basic condition. But later on, we'll see like acidic condition, oxymercuration reaction, and that's undergo the acidic condition. Right, so the take-home message here is the keto-enol tautomerization will take place under either basic or acidic condition. The keto form is more stable compared to the enol form. Or if you're looking at these reaction mechanisms, whenever you see a enol, so a double bond, and then around that double bond, you have like a OH group. So whenever you see an enol, keep in mind that the keto-enol tautomerization can take place. All right, yes.
And this is very minor detail, but on the last step of the acidic condition, you put the electrons from the bond from oxygen onto hydrogen. Wouldn't it be
Yeah, it should be the other way around. Thank you. All right, so this is like two things to keep in mind. One thing is whenever you see a enol, keep in mind that keto-enol tautomerization can take place. This is like what we did in our previous example. Whenever you see a free carbocation, keep in mind that 1,2 shift or the carbocation rearrangement can take place. So these are the small points that are easy to miss when we're asking you to predict the reaction outcome or to write the reaction mechanism. Yeah.
So you said that both resonance structures contribute, so could you go off of either one of them?
Well, so this one is like, the first step is like protonation, right? So basically from here, if you deprotonate, you're just going back to the original starting material. It's the same. Like if you're taking this one and you're just going back to the original reactant. Okay, so coming back to hydroboration oxidation. So far we went over hydroboration hydration or hydroboration oxidation of an internal alkyne, meaning internal alkyne will have same stereoselectivity, a little bit of regioselectivity control, and we don't worry about overreaction. But if we're looking at terminal alkynes, so that is saying when we have, let's say, this one, when you have a terminal sp carbon-hydrogen bond, and you're reacting that with a boron reagent. So the terminal hydroboration, which a small boron reagent, will form an alkene that is not sterically hindered, meaning we have a terminal alkene that still have like a CH group around it. And this can potentially undergo overreaction to form the diboronated species. All right, so for terminal alkynes, reacting that with hydroboration reagent will tend to have overreaction. So to prevent dihydroboration from taking place with terminal alkynes, you want to use different substrate. So these are two typical boron reagents you can choose from that are sterically hindered and can prevent the dihydroboration from taking place. Or the other way to put it, like if I want to end up with an aldehyde, what should I do? We should first react my terminal alkyne with a sterically bulky HbCl2 or the dicyclohexylboron to form this terminal alkynyl boron reagent. And the bulkiness of my Cl group, or the sep isoamyl boron, will prevent this alkynyl boron to undergo a second hydroboration reaction. After this, treatment of the alkynyl boron group with hydrogen peroxide and NaOH will give us a enol. the enol can undergo the basic condition tautomerization to form my keto form. Or in this case, since we're dealing with a terminal alkyne, we're forming a aldehyde. All right, so that means in organic chemistry, in this case, if we start from an alkyne, we are either gonna get ketone or aldehyde as our product. If we start from internal alkyne, we'll eventually get ketone as our product after the keto-enol tautomerization. If we start from an alkyne with a terminal CH, that means we want to treat it with a sterically bulky boron group, and then treatment of hydrogen peroxide and NaOH will give us an aldehyde as a product. I'm a little run short on time, so I'll take any questions you might have outside after the class. But I do want to finish up on our acid catalyzed hydration or mercuration with you. So that's a hydroboration. Remember, hydroboration is slightly regioselective, syn addition. For oxymercuration or acid catalyzed hydration, now if we look at the reaction condition, now we're looking at an acidic condition, reacting that with the alkyne. So whenever you write this one as like together, we're saying this is, both of them are in my reaction mixture. But if we're writing it in this case, we're saying we're having two separate reactions. We do the hydroboration first, and then we add the hydrogen peroxide and NaOH after the first reaction is completed. So in this case, we can ask you to write out what is the reaction mechanism. So this one will start by reacting it with a mercury 2+. And this is going to form our bridged intermediate again. So when the nucleophile comes to attack, where in this case my nucleophile is just my water. So my nucleophile comes attack again, or attack from, again, the opposite site, and the major contributor from my resonance structure. And the product here will be my CH3 attached to carbon. My oxonium ion must be trans to my mercury and hydrogen. All right, so if we look at the regioselectivity, my Hg plus is on my less substituted carbon. And my oxonium cation will be trans to my Hg plus. Our next step here will be my proton transfer or deprotonation. So that is, we're taking the electron, we're taking the proton to form my neutral enol form. And remember, whenever you see an enol, the enol will undergo tautomerization to form the keto form. So in this case, we'll be forming the carbon, oxygen, CH3, CH2, Hg plus. I did not write out the full tautomerization mechanism, but you can find that tautomerization mechanism under acidic condition in our previous slide. And then from here, the next step, we're gonna lose my Hg plus. And then eventually form my product here. So under acidic condition, the overall product here, we're getting, again, a ketone as our product. So what's the difference here? So the difference here is that under the hydroboration, because my OH is on the terminal carbon, so we're forming the aldehyde as a product. For the acid catalyzed hydration, we're forming the ketone as our product because my OH is on the internal carbon. All right, so you'll be able to find my fall mechanism that's much more well articulated in our annotated notes. And basically in here, I skipped a few steps of like actual protonation of the OH and then keep going, yeah.
So the Hg electrons that go to that bond, is that those electrons making?
So this one will form, let me not skip any step. This one will eventually form this one, carbon O minus, double bonded, CH2. And under acidic condition, this will become your CH3, carbon, OH, by adding a H plus, and CH2. This is, again, one of your enol, and this will undergo a second tautomerization to form the final ketone form. All right, so two tautomerizations are taking place in this acid catalyzed hydration or mercuration reaction. But still, I think my annotated note did a better job in writing out this full reaction mechanism. Yeah.
Are we expected to draw each of these intermediate steps on the exam, or like?
Well, it depends on how we ask you the question. If we ask you to draw the full mechanism, then yes. If we ask you to only predict the product, then you don't have to draw the full mechanism. All right, a last reaction of alkyne are reduction or hydrogenation. So we're adding hydrogen onto the alkyne to reduce it into alkane or alkene, right? So alkane, single bonded, or alkene. So the take-home message here is depending on the reaction condition, we can control to what degree the reduction takes place. For example, if we're doing the reaction under the condition of H2 and palladium as our catalyst, it's really hard to control, the reaction so it stops at the cis alkene. That means if we're treating the reaction with H2 palladium, we're fully reducing my alkyne into alkane, right? So full reduction is saying reducing my alkyne all the way into alkane. Alternatively, if we use a pretty complicated catalyst called Lindlar's catalyst, I don't expect you to know what is the composition of Lindlar's catalyst, but using the Lindlar's catalyst, we'll be able to only reduce the alkyne into cis-alkene. So the most important take-home message here is depending on the reaction condition, you can control the product, right? So H2 palladium, full reduction into alkane. Lindlar's catalyst is reduction from alkyne to cis-alkene, and stop here. No reaction to alkane. All right. The other way to reduce my alkyne is called the hydroboration protonolysis. So this is like a follow-up of the hydroboration reaction. So we went over the hydroboration reaction, right? So you can add a boron reagent to an internal alkyne to give a trialkynoboron. And again, like if we're using BH3 as a reactant, we're seeing adding the BH3 onto the alkyne to form this alkynoboron. Then instead of treated with hydrogen peroxide and NaOH, if the condition is treating it with acetic acid, we will end up by replacing the boron with hydrogen to form a cis alkene. So there are two different ways we can transform alkyne into cis alkenes, either using the hydroboration protonosis or the reduction with the Lindlar's catalyst. All right, so two ways to reduce your alkyne into cis alkene. One way to reduce your alkyne into alkane, the fully saturated hydrocarbon, that is your H2 and palladium catalyst. And one more reaction is eventually maybe we want to have a trans alkane as our product. So this is called the dissolving metal reduction. So that is reduction of an alkyne with sodium or lithium in liquid ammonia will be able to convert an alkyne into an alkene with anti-stereoselectivity, meaning we're adding the two hydrogen on trans position of my alkene. So this is dissolving metal. So we're dissolving a alkali metal, whether it's sodium or lithium, in liquid ammonia. The reaction will convert a alkyne into a trans alkene. We'll go over the mechanism of the dissolving metal reduction in our next lecture. And then also in our next lecture, we'll do several examples together called the retrosynthesis process. And our midterm 2 will likely cut to finish our alkyne chapter, which I believe is chapter 7. So your midterm 2 covers everything from acid-base chemistry all the way to chapter 7. All right, and we'll finish discussing chapter 7 in our next Monday's lecture. All right, and I'll post more information regarding your midterm 2 in our next Monday, probably before lecture as well.